In this presentation on real numbers, we are going to discuss some general proofs related to irrational numbers. Now, in our previous presentation, we have already discussed this lemma. It states that let p be a prime number and a be a positive integer. Then, if p divides a square, then we have shown that p divides a. We have proved this lemma. So we are going to prove this, use this lemma to prove the next result. Now the first result we have is, if p is a prime number, then we have to prove that square root p is irrational. So we suppose that we have a prime number p, and if possible, we have to prove that square root p is irrational. So we are going to use the method of contradictions to prove this result. So we suppose that if possible, let square root p be rational, and if it is a rational number, then it can be represented in the form p by q, or in this case we are saying it can be represented in the form m by n. We are writing m by n because p is already used in this notation over here. We are not writing p by q over here, we are using m by n, and we are saying that this is the simplest form. It means that m and n, they are co-prime, and we have n is not equal to 0. Now we have this equation. We are saying square root p is equal to m by n. Now if we square both sides of this equation, we get p is equal to m square by n square. Now shifting this denominator on the left hand side, we obtain p times n square is equal to m square, and suppose we are saying this is equation number 1. Now if we have p times n square is equal to m square, we have, look at this term over here, it is p n square. It means we have p divides p n square, and if p divides the left hand side of the equation, it means that p divides the right hand side, that is m square. And by our previous lemma that we have discussed, we have p is a prime number, p divides m square, it means that p will divide m. So what we have obtained is that this implies us that p divides m. Now suppose we are saying if p divides m, then we have some integer q such that we can write m is equal to p times q. We are saying p divides m, it means we can write m is equal to p into q for some integer q. This is by the definition of divisibility. So if we substitute this value of m in equation 1, we substitute m is equal to pq in equation 1. This is equation 1 we are saying. We are substituting this value of m over there. We obtain that p n square is equal to p square q square. This p gets cancelled. This p is there on both on left hand side as well as on the right hand side. So what we obtain from this is that this implies us n square is equal to p times q square, because p is a prime number, so clearly p is not equal to 0. So we obtain that n square is equal to p times q square. Now what this thing implies, we are saying p divides pq square. It means that p divides n square. We have this p is there in this term pq square on the right hand side, so it means p divides pq square. So if p divides the right hand side of this equation, then clearly we have p divides n square, and because we have p is a prime number and p divides n square, so this implies us that p divides n. So what we obtain is if p divides n square, then p divides n. Now look at these two terms. We have p divides m, we have p divides n. It means that p and q, p is the common factor between m and n. We are talking about these two terms, p divides m, p divides n. It means that p is the common factor of m and n. And this is contradiction to the fact that m and n are co-prime. We have considered that m and n are co-prime, so we are saying that this contradicts the fact that m and n are co-prime. And this contradiction is arising because we have assumed that square root p is rational. It means that we cannot assume this thing, so we obtain that square root p is an irrational number. Now next we have is, if a is rational and square root b is irrational, we have to prove that a plus square root b is irrational. So suppose again we are proving it by the method of contradiction. We are saying that this term a plus square root b, let it be rational. If possible, let this term be rational. Then we have what we have obtained over here, that a plus square root b is rational. We have assumed this thing, and it is given that a is rational. So if we subtract two rational numbers, we know that the answer must be a rational number. We are saying we have one rational number is a plus root b, second rational number is a. If we are subtracting these two terms, the answer is rational, because we are saying the difference of rational numbers is a rational number. So what we obtain from this is, this implies us a and a gets cancelled, this a and this minus a, these two terms get cancelled, and we are left with this square root b is rational. But it is given over here that square root b is irrational. Look at this problem over here. It is given that if a is rational and square root b is irrational. But what we have obtained, that square root b is rational. It means that we have obtained the contradiction. This contradiction is due to the fact that square root b is irrational. And why this contradiction is arising? Because we have assumed that this term, it is rational. It means that we cannot assume this thing. Hence we are saying that a plus square root b is irrational number. Now the next question we have is, if a is a non-zero rational number, it is a rational number, and square root b is irrational, we have to prove that a square root b is irrational. So we prove this by the method of contradiction, and we suppose that this number a square root b be rational number. And if it is a rational number, then its simplest form, it is, we are supposing this thing, that its simplest form, it is p by q. This is simplest form, means we are saying p and q are co-prime or relatively prime, and p and q both these are integers. Now from this term, we are saying a square root b equal to p by q. We obtain the value of square root b as, it is equal to p, this is the numerator, and divide it by a into q. This a we have shifted on right hand side. So we are saying, suppose this is equation number 1. Now what we have is p and aq, the numerator p and this denominator aq, these both are the rational numbers, and aq we are saying it is not equal to 0. It means that this number p by aq is rational. Why we are using the term rational in place of integers is because a is a non-zero rational number. So clearly this a into q, this will be a rational number. So we are saying p and aq both are rational. So p by aq is also a rational number. Now if p by aq is rational, we are talking, look at this equation 1 over here. We are saying p by aq is a rational number. It means square root b is also rational. So what we are saying, that in view of this equation 1, we have square root b is the rational number. But look at this problem over here. It was given that square root b is irrational. It was given. So we are saying that this thing, it contradicts the fact that square root b is irrational. So what we obtain is the contradiction that we have arrived over here. It is arising because we have assumed that a square root b is rational, and hence we are saying that a square root b is an irrational number. Next we have is prove that square root p plus square root q is irrational where p and q are primes. So again, we prove this by the method of contradiction, and we assume that this number square root p plus square root q, it is a rational number. Now if it is a rational number, then there exist co-prime numbers a and b such that we can write square root of a plus square root of b is equal to a by b. Now if we shift this term square root of q on this side, we obtain the value of square root p, that is equal to a by b minus square root of q. There are two square roots over here. We want to make one of these terms free from this radical sign. So we have calculated the value of square root p. Now if we square both sides of this equation, we obtain square root of p square, that is equal to a by b minus square root of q whole square. We have done the squaring on both these sides. Now when we square this term, look at this term, it is square root of p square. The value we will obtain, that is p, and right hand side it is a minus b whole square. So it is a square minus 2ab plus b square. B square means we are saying square root of q whole square. That value will become q. Now we have only one term, this square root q with the radical sign. Now if we calculate the value of this term, we obtain, this implies us that 2a by b into square root q, we have shifted this term on the left hand side, we have shifted this p on the right hand side, and we are saying that this value is equal to a square by b square plus p minus a plus q minus p. So the value of square root q that we have, it is equal to a square plus b square q minus b square p. We have taken the LCM b square over there. Then this one b square and b gets cancelled. We have b square and this b. We have taken the LCM over here. This b square and b gets cancelled. And we are left with is into b by 2a. Because we have b is not equal to 0, so we can divide this whole equation by b. So we are saying that this value is equal to a square b plus b cube into q minus p divided by 2a. Now all these terms, we are saying all these terms a, b, p, q, they are integers. These all values a, b, p, q, these numbers we are saying, these are all integers. It means that this whole term a square b plus b cube into q minus p divided by 2a, this term, it is a rational number. So we are saying square root of q, that is equal to this value, and this value on the right hand side, it is a rational number. So this implies us that this value on the left hand side is also a rational number. So we are saying square root q is also a rational number. But look at this problem over here. It was given that p and q, they are prime. It means q is a prime number. So we are saying that if q is a prime number, then we have already proved that square root of q is irrational. This thing we have already proved. So what we get from this is that there is a contradiction over there in this case. This thing that we have proved, that square root q is also a rational number. What we have is square root q is irrational because for any prime q, square root of q is irrational. So we have reached a contradiction. We are saying since a contradiction arises, so it means that our supposition is incorrect. The supposition we have made over here, we have assumed that this number is rational. This supposition is incorrect. So we are saying that hence this number square root p plus square root q is an irrational number.